Hello everybody, welcome to the Advanced Photon Source. My name is Dr. Antonio Lanzirotti, people call me Tony, and I'm one of the beamline scientists here that do experiments using the facility. I'm going to sort of assume that a lot of you don't really know what a synchrotron is, so let me just give you a couple minutes about an introduction about how the APS works and what it does and why scientists come here to do experiments. So the Advanced Photon Source at Argonne National Laboratory is a particle accelerator. So typically, when a lot of people think about particle accelerators, they think about atom smashers, things like CERN and the Large Hadron Collider, which people have something you may be somewhat familiar with. This is a little bit different. So rather than taking atoms and accelerating them to smash them together to look at the nature of subatomic matter, what facilities like the Advanced Photon Source do is they take electrons and then they accelerate them near the speed of light in a very large storage ring. And as the electrons are accelerated by magnetic fields, they release energy, and that energy is in the form of light. And here at the Advanced Photon Source, that light that we use is primarily in the X-ray range. And it's very, very high brightness and very, very high flux. There's lots of photons that are being generated. And then we can use that light to do a variety of different kinds of experiments. So the Advanced Photon Source is operated by the Department of Energy. The Department of Energy operates 4 of these types of facilities throughout the United States at different national laboratories. The one here at the Advanced Photon Source is the largest of the 4 that the Department of Energy operates, and operating at the highest energy. So at the APS, the way the electrons are steered around the storage ring are by magnets, right? Dipole magnets that are around the ring. The circumference of the ring is about 1 kilometer. And every time the electrons are accelerated around the storage ring, that energy is released, and you can put a station there to collect that radiation to do different kinds of experiments. So those are the dipoles that steer the electrons around, and then between the dipole magnets, what we call the bending magnets, there's also other periodic magnetic devices that take the electrons and also accelerate them in a very short period. That can produce radiation that's much, much higher brightness by orders of magnitude compared to what the dipoles can do. So at the APS, there's something like about 40 sectors, 40 times that we steer the electron beam around. And then at that sector, we can put multiple beam lines. So at the APS, there's something like more than 60 beam lines that are taking use of radiation operating simultaneously to do different kinds of experiments. And those experiments can be in material sciences. They can be in biological sciences. And then here, we're at Sector 13. This is operated by the University of Chicago. And our emphasis is on earth and environmental sciences. So we mostly do geoscience research for different kinds of experiments. Okay? So I'm going to take you through some of the stations that we use here. So we actually have 5 beam lines here at Sector 13, 3 of them which use these insertion devices, these very high brightness sources to different kinds of experiments. And the experiments we do make use of looking at how materials absorb the X-rays. We look at how materials are excited, look at the spectroscopy of materials, and then in some materials, as X-rays travel through them and they diffract, that can tell you something about the crystalline structure of materials. Okay? So this is the first station. This is 1390E. So this is an X-ray microprobe. So from where we are in this station, the X-rays where they're generated are about 50 meters up that way. So there's a lot of instrumentation and optics from where the X-rays are actually generated from the insertion device periodic magnets to where they come into the hutch here. So the hutch is actually a steel enclosed room, and inside the steel walls is actually lead. So you can't be in here when experiments are going on, right? And so the way we do that, everything's done remotely. So we go through a search procedure, and the radiation is very intense. It'll be kept in here. So for this station, the X-rays come through this little port here. So the X-rays that come into the station, we can actually change what the energy of those incident X-rays are. We have optics upstream that do that. They're about, roughly about 0.5 millimeter in diameter. So what's unique about this station is that we actually have optics here. So these are silicon mirrors. I'm just going to go a little closer. So in this box are two pieces of essentially optically flat silicon, okay? And so X-rays, unlike, you may have heard of like electron probes. So in electron probes, they use magnetic fields to focus the electrons onto a sample to do analysis. So X-rays don't, they have no charge, so you can't do that. So the way we focus magnets is using different kinds of optics. So with these, what are called Kirkpatrick Baez mirrors, we use total external reflection off of the silicon. So the X-rays will, these pieces of silicon are put at a glancing angle, only about, a couple of milliradians in pitch. So the X-rays actually reflect off of the surface of the silicon. And you can't, they don't look bent, they look very flat, but this whole assembly, this stainless steel assembly, actually pushes on the silicon to give it a slight elliptical bend. And because it's elliptically shaped, all the X-rays will focus to a different point. And by changing the shape of that ellipse, we can take those X-rays that are half a millimeter in diameter coming into the hutch and focus them to a sample to only about 1 micron in diameter. So human hair is about 100 microns. So we'll put something like 10 to the 12 photons X-rays per second onto a point on a sample that's only about a micron in diameter. So the sample sits here. The user gets an optical view just like a regular microscope, but then you can do different kinds of experiments. One of the things you can do is actually look at the chemical composition of the material, because if the X-rays are energetic enough to knock out the inner shell electrons out of the atoms of interest in a sample, that atom becomes excited, and then it'll take electrons from higher orbitals to fill the empty shell, which will then generate characteristic X-rays that we can detect. And that will tell us about the composition, how much of that element is in a sample. And that is then detected using a solid state detector. This is a 7-element silicon drift diode array. So the X-rays are emitted from the sample because of that excitation. They're detected in this solid state detector. And because we're using so many photons, we can actually look at concentrations in the material down to the parts per million or parts per billion detection sensitivity, okay? And then if you, again, you can't really move the X-rays around, but you can move the sample around. So if we then raster the sample through the X-ray beam, we can actually make a compositional map of the distribution of those elements in the sample, all right? The other thing that's very interesting about that is, again, the X-rays, when they're generated from the insertion device, from the source, they're what we call white light, right? So that's broadband. It has lots of energies of X-rays, focused around the harmonic of the undulator, but there's a lot of X-rays in there. The monochromator, we can actually select out a specific energy of X-ray, and then we can actually change it. So what we can do is we can actually take the X-ray beam and scan its energy so that it goes through what we call the binding energy of a particular electron in an atom. So for example, if you're interested in chromium, right? A lot of environmental scientists are interested in chromium because hexavalent chromium is supposedly has more toxicity than trivalent chromium. And you might want to look at very low concentrations of chromium and look at what its valence state is. So X-ray absorption spectroscopy is something that you can do on these kinds of samples using this instrument. So what you do is you change the energy of the incident X-ray. When you're below the binding energy for knocking that inner shell electron out of the atom, most of the X-rays are travel through the sample. There isn't much absorption. But as you go through the binding energy, then you'll get a spectra, right, that shows how that X-ray, that X-ray is absorbed and how that electron is emitted. So with that, you can actually then look at the valence state of different elements, look at the speciation of different elements and materials, look at things like chromium and arsenic and iron and sulfur, and you can do that all with a spot size of only about 1 micron and at concentrations that are in the parts per million range. So for environmental sciences, that ends up being very useful. For a lot of earth sciences, that ends up being very useful too. And the big thing for doing this with this type of instrument as compared to other types of particle beam techniques, electron probe or laser ablation systems, is that you can see that here the sample sits in air, right? Because X-rays are very penetrative, the sample doesn't have to be in a vacuum. It doesn't have to be carbon coated. It doesn't have to be sectioned in any special way. You could actually do whole live plants and do that same kind of experiment, right? And that's something that's really unique for these kinds of instruments. You can't really do that with another type of particle beam method. Okay? So that's the X-ray microprobe. Let's go to the next station. So in environmental sciences and earth sciences, we want to understand, the chemistry of elements in different kinds of materials of interest. But also when we think about the chemistry of materials in the earth and what happens is particularly in environmentally sensitive samples, a lot of those reactions happens on the surface of minerals, right? So you have a mineral surface and you might have a fluid that travels over that mineral surface that has some element of interest in it. And then that chemistry, the most interesting chemistry, happens right on the surface of the mineral. So one of the things that's very interesting is looking at techniques where you can actually look at how those elements are bound right at that surface, and that surface may only be a few angstroms thick. Okay, so the way we do that is using these sort of a scattering technique. So rather than trying to focus the beam to a very small size and doing a point analysis, with this instrument, what we do is we look at the scattering of X-rays off of the mineral surface as the mineral surface composition changes, and we want to do that with very high angstrom precision. So the way you do that, if you want to take a small mineral surface and orient it with very high precision, you need a device that's this big, okay? So this is a multi-circle goniometer. And these are motors that help orient the sample in multiple dimensions. So you can rotate the sample on this axis, in that axis, in this axis. You can move the sample around. So the sample would sit on a point here. This will be put into the X-ray beam. And then you can very precisely orient the sample so that you know that the X-rays are just grazing off of the surface. And then you can do chemistry on that surface and actually look at how the chemistry, either using X-ray diffraction techniques or in some cases actually doing similar kind of X-ray absorption techniques, look at how that chemistry changes on an angstrom by angstrom level. So an interesting experiment that was done here that sort of makes use of that technology, being able to do that, is a NASA project that looked at the composition of solar wind. So about 20 years or so ago, NASA launched a number of probes to actually, sort of cheaper to go out and collect extraterrestrial materials to come back and analyze them. One of them was a probe called Genesis, which actually went out to collect solar wind. So it actually collected solar wind embedded into these detector samples, and then that sample was brought back to Earth, landed, to be analyzed. Unfortunately, one of the things that happened with that mission is that on the return to Earth, the parachutes failed and the space probe actually crashed into the desert. Okay, so now you have these samples that have solar wind particles collected that they want to analyze, but it's also contaminated with all the dirt from the crash site. So one of the things that they were able to do is to bring those samples here, and then using this sort of grazing incidence analysis, basically, angstrom by angstrom at a time, actually go into the sample collector and determine what is contaminant from what is embedded into the sample below. Okay. And again, that's being able to do these types of analyses with very high detection sensitivity, very high flux rates, and being able to very precisely orient samples into the beam for analysis. Okay. Okay, one more. So the other two beam lines that we talked about, we mostly talked about chemistry and things that are more relevant. A lot of the scientists that come here to do experiments are interested in the chemistry of the Earth's surface. But of course, as geoscientists, and we're talking about the composition of the Earth and the planets, most of the Earth we can't actually get to, right? It's the deep Earth. What's happening in the mantle, what's happening in the Earth's core. So this station is actually designed to actually help us probe those very deep parts of the Earth by synthesizing materials at pressure and temperature, and then because we're using X-rays that are penetrative, being able to go through the devices that we're using to simulate those materials and actually do the analysis in situ, change the pressure and temperature conditions, and then see how the structure of those materials change in real time. So here we have two devices to do that. One is a multi-anvil cell. So that's this big blue press back here, okay? So what you can do here is you can take bits of material and they go into this sort of jigsaw puzzle type assembly. This gets put into this hydraulic press, and then that pushes together a set of anvils, slide together like a jigsaw puzzle to compress the material. So with this, we can actually get down to sort of, mantle pressures and temperatures with fairly large materials. And a lot of the experiments that get done here are X-ray diffraction. So we talked about, scattering in the last station, and then we talked about X-ray absorption and fluorescence in the first station. With X-ray diffraction, it's a scattering technique, but what happens is the X-rays will go through the material, and then depending on the crystal structure of the material in the sample, the X-rays diffract, and then from that diffraction pattern, you can actually get the crystallography and mineralogy of the sample. So that's one thing that we can do with the multi-anvil cell. They can also do just regular absorption imaging. So you can actually, just like a conventional medical X-ray, you can look at the structure of the material as you put pressure on it and actually take images of the sample as it changes. You can actually, and again, because we're using X-rays and we can go through the sample, you can actually rotate the material to do what we call tomography. So it's like a CAT scan, right? So, when you go have a CAT scan, what they do is they have an X-ray source and a detector, and that spins around the patient to actually collect a series of X-ray images, and then using computer techniques, you can reconstruct in 3 dimensions the structure through the sample. We can do that here at pressure, in cells, with very high spatial resolution. We can get resolutions here that are, at sort of the micron scale, which is difficult to do with conventional medical sources. And because we have so many X-rays, we can go through very dense materials. We can go through rock, okay? So the other device here for looking at the structure of very deep Earth materials, we take a very different approach, a slightly different approach here. This is called a diamond anvil cell station. So here the X-rays are again focused, they're fairly small, but then what we do is that we take material of interest and we put it, if we want to generate the types of pressures that we have in the very deepest part of the Earth or in some of the largest, the large planets, you want to be able to generate forces that are high enough to do that. And the way we tend to do that is by taking little bits of sample and putting them in what's called a diamond anvil cell. So if you look at this assembly, and I'll have them, right, there's 2 gem quality diamonds here. So if you put a little bit of material between the diamonds, and since pressure, is force over unit area, the diamonds are very strong, you can squeeze the diamonds together, and then where the sample is in between the diamond tips, you can generate pressures in the, at very high levels that are more synchronous with what you're doing and you would have in the Earth's core. And again, because diamonds are X-ray transparent, the X-rays will go through the cell, they will go through the diamonds, they will go through the sample, and then diffract. And then you can have an area detector to look at the diffracted signal, and then that will tell you what the crystallography is. But then you can also then change the pressure if you want to look at how the structure changes, or you can actually heat the sample. So we can take a high-power laser, put the laser through the diamond cell as well, actually, and heat the sample up to actually look at how the material changes with respect to temperature. Okay. So those are the 3 insertion device stations that we do here. We do a large number of experiments. We operate basically 3 months on, right, and then a month break. Before the whole COVID thing, scientists came. They came here from all over the world to do experiments. So they would actually come themselves. They would spend 1, 2, 3 days here to do an experiment. Because this is operated by the Department of Energy and it's paid for by tax dollars, there's no fee for most of the beamlines here to be able to come here and do an experiment. You would propose to do an experiment, say this is the experiment I want to do. That proposal is reviewed by other scientists, your peers. It's scored, and then based on that score, you're given some beam time to come here and do an experiment. And the idea, the reason why it's free is that that information is going to be in the public domain. You're going to publish it, right? So it's a benefit to everybody. And again, here we just saw 3 stations. We operate basically, 3 months, 3 months, 9 months out of the year with users, basically 24/7 more or less, right? We have a day off once a week for machine studies. And this is, we operate 5 beam lines, but now extend that out to more than 60 across the whole ring, right? Everybody doing experiments all at the same time in a very similar kind of mode. And I think it just gives you a sense of the amount of science that gets done at a facility like this. Okay? I think I'm done.